Hey guys, this is a quick video just to give you the basics of 2D motion. So you're experts at 1D motion now and you want to move to 2 dimensions. And the thing I'd invite you to think about is flipping a coin. So if you flip a coin standing on the ground, that's probably a pretty familiar experience. But you'll find that it's the same experience you have if you flip a coin on a train or an airplane or in a convertible while you speed off, spewing terrible smoke into the atmosphere. In either case, the flip of the coin doesn't really seem to be affected by your motion backwards and forwards. You get more or less, minus wind resistance, the same experience moving in a car. So let's take a look at what that looks like. If you're standing on the ground, well, the coin goes up and then it comes down. It's pretty straightforward. If you're in the convertible, though, again, ignoring wind resistance, as you move along, the coin goes up, but it's got to move with you in order to keep up with you. So it makes this sort of arcing motion. Somehow the coin knows to move just the way you move and to move up the same way it would move if you're standing at the ground, so that you can't really tell the difference whether you're moving or not. This is because motion in the X and motion in the Y direction are independent from one another. That's because they're in perpendicular directions. So here's another thing to consider. You've got two balls. They both start out at a certain height, right? One is just going to be dropped from rest. The other has an initial speed to the right that's indicated by that arrow there. So we know that both balls are going to be accelerated downward by gravity. And so after a little bit of time, they both fall the exact same amount, and they've both sped up a little bit because they're being accelerated by gravity. The red ball has also moved to the right. You go again. Now those green arrows are a little bigger because gravity's pulling them down a little faster. And meanwhile, the orange arrow has stayed exactly the same because I'm not doing anything in the X direction. I go again and again. You get the idea. If you look on the left, the ball falls faster and faster downward. If you look at the ball on the right, the red ball also falls faster and faster downward, but it moves to the right at a constant rate as it does so. The quintessential example of 2D motion is projectile motion. Projectile basically means something gets shot out of a cannon, and then after that, the only thing that acts on it is gravity. So we have a sense of what this is going to look like. The cannonball is going to trace out some sort of parabola looking like thing. You're going to get some sort of curve for it. Let's look a little more carefully. When it shoots out of the cannon, that green arrow represents its speed. The speed, the velocity, has to point in the direction of motion. Things move the way their velocity tells them to move. So a couple of things are happening here, you notice. The direction of the velocity is changing because the path changes direction, and also the size of the arrow is changing, right? So if the size of the velocity is changing, that must mean there's some acceleration. And indeed there is. At every single point on this path, gravity is accelerating the projectile downward at 9.8 meters per second. Doesn't matter where the projectile is or how fast it's moving, it's always being pulled down at 9.8. Let's see what that does to the velocity vector by breaking that into components. So it starts off on the left, it's moving up and to the right, and those arrows are about the same. But as gravity does its work on it, the upward arrow decreases, and the green arrow rotates down toward the purple arrow because that's where most of the speed lies. At the very top, all of the velocity in the Y direction has been taken away by gravity. All of the speed points to the right. Notice the purple arrow never changes because gravity is perpendicular to it. It doesn't change its speed. What happens next is it accelerates downward, so that yellow arrow grows again, and the velocity, the green velocity vector, ends up pointing down in basically the opposite direction that it started out. If we want to get technical and put some math here, call the green arrow V0 when it launches. So we can analyze the motion in the X direction by using our kinematics formulas that we've derived earlier. Our initial velocity, well, that's the component of that green arrow that lies along the purple. That's V0 cosine theta. The acceleration in the X direction is 0, and we may as well say that it starts at x0. We do a little bit of rearranging, and this is what the motion in the X direction looks like. Well, what's going on in the Y direction? Same exact kinematic formula. The laws of physics are the same up as they are left and right. Only in this case, the initial velocity is V0 sine theta. The initial acceleration is negative g. So I've actually got something going on here. And now my formula looks like this. If I say, well, I'm not really interested in what's going on with the time, is there a way to eliminate that? Sure. You end up with this. This is, if you look at it, y equals ax plus bx squared. This is the equation of a parabola, and because the coefficient of the x squared is negative, it inherits that from g, by the way. Because the coefficient of x squared is negative, it's an inverted parabola. I hope that this helps explain some of the features of 2D motion.